Hello there, and welcome to the second part of our Fibonacci numbers discussion. So in this video, we're going to continue our discussion of the Fibonacci numbers and discuss a few more properties that some people find interesting and also have applications in several other number theory fields. So remember, the Fibonacci numbers is defined as the sequence 0, 1, and from there on is the sum of the preceding two Fibonacci numbers. So also in the last video, we proved that the generating function for the nth Fibonacci number is going to be equal to phi to the power of n minus negative phi to the power of negative n, all divided by the square root of 5, where phi represents the golden ratio. So in this video, we're going to continue building properties for the Fibonacci numbers and its connection to the golden ratio. Alright, so let's start off by stating the first theorem. Alright, so let's see. So if k is large enough, then the k plus 1th Fibonacci number is going to be approximately equal to the kth Fibonacci number multiplied by phi. So what exactly does this mean? So the next Fibonacci number is pretty much just a multiple of phi from the Fibonacci number that we're on, right? So the Fibonacci numbers are just multiples of phi in a way, right? Assuming k is big enough. So how can we sort of prove this? Well, another way we can rewrite this is k plus 1 divided by f of k is going to approximately be equal to phi, where k is large, right? So in a way, phi is the asymptote of the quotient of the functions phi k plus 1 and phi k, or fk plus 1 and fk, right? So it's pretty much an asymptotic. So we can use limits to prove this, right? So proof. So our goal is to show that the limit as k goes to infinity of fk over 1, fk is equal to phi. So how can we do that? So we know the generating function for the Fibonacci numbers already, right? They're both over the square root of 5, so we just sort of cancel when we divide that. So we're going to have phi k plus 1, and then we're going to have minus phi to the negative k plus 1 over. Then we're going to have phi k minus phi to the minus k, right? All right, so phi is a positive number, and even if it's not positive, we have a negative term here. But we have a positive number raised to a negative power, and k is going to get arbitrarily large. So in the limit, we know that these things are going to go to 0 as k goes to infinity. So that means in the limit, this is just going to be equal to the limit as k goes to infinity of phi k plus 1 over phi k, which is just going to be equal to the limit as k goes to infinity of phi k times phi over phi k. And as we see, these phi k's cancel, and we're just equal to phi as the limit, right? So a very, very easy proof, and you can do some algebraic justifications if you're not comfortable with that type of manipulation, but that's just an asymptotic in a way. All right, so let's just recall a couple properties from basic pre-calculus. For example, the sum of integers is going to be n times n plus 1 over 2. The sum of squares is going to be n plus 1, 2n plus 1 over 6, and there's a few others that we derived back then, right? So what about the sum of Fibonacci numbers, right? So that's going to be the next theorem that we take a look at. So the sum from k is equal to 0 to n of f of k, where f is the Fibonacci number, is going to be equal to the n plus second Fibonacci number minus 1. Now, why is this formula so useful? Well, we already have a generating function for the Fibonacci numbers, so we just plug n plus 2 into that formula, subtract 1, and that'll be it. So also it says that the sum of Fibonacci numbers is always one less than another Fibonacci number later on in the sequence, which is pretty interesting, right? So the sum is always one less than another Fibonacci number, right? So proof. So let's do mathematical induction on this, right? So I'm going to consider n is equal to 0 first for our initial case. So f of 0 is going to be equal to 0. So that is the 0th Fibonacci number, right? Which is of course equal to the second Fibonacci number minus 1, because the second Fibonacci number is 1, and 1 minus 1 is equal to 0, so that passes, right? So for our induction step, so we're going to assume that the sum from k is equal to 1 to n of fk is equal to fm plus 2 minus 1. So let's go for the extension step. So that means the sum from k is equal to 0. Now notice I don't really care if I start at 0 or 1 because the 0th Fibonacci number is 0, and 0 plus anything is just going to be itself. So it doesn't matter if you start off at 0 or n, but I'm just going to start off at 0 just for completion. Right? So let's go to m plus 1 of f of k, which is just the same as the sum from k is equal to 0 to n of fk plus fm plus 1. So we've already assumed that the sum from 0 to n is fm plus 2. So this is just going to be equal to fm plus 2 minus 1 plus fn plus 1. Right, and we can do some rearrangement here. So this is just going to be equal to fm plus 2 plus fm plus 1 minus 1. So this is the sum of consecutive Fibonacci numbers, which is going to be equal to the next one in sequence, right? Because a Fibonacci number is the sum of its preceding two. So this is just going to be equal to fm plus 3 minus 1. So that is pretty much what we were trying to prove. Since the difference between n plus 1 and n plus 3 is 2, this completes the proof of that theorem. Alright, so the next property is related to linear algebra. So consider the matrix 1, 1, 1, 0, right? And suppose we square this. So this is a very easy computation that you can do on your own time, right? So once we perform this, it's very easy to see that this is just going to be equal to 2, 1, 1, 1, right? And you can do 1, 1, 1, 0 cubed as a practice problem. So that's just going to be 2, 1, 1, 1 multiplied by 1, 1, 1, 0, right? Which we can find to be equal to 3, 2, 2, 1. Now, you can do mathematical induction on this property to some integer n. So 1, 1, 1, 0 to the power of n, you can actually find to be equal to fn plus 1, fn, fn, fn minus 1, right? Now that is a interesting result, but it's actually not too hard to prove, and you can do mathematical induction on this, but it requires some comfortability with multiplying matrices, right? So we're going to use this to derive another property. So we have two matrices, right? So if two matrices are equal, then the determinant of those matrices are also equal. So the determinant of the matrix 1, 1, 1, 0 to the power of n is going to be equal to the determinant of the matrix fn plus 1, fn, fn, fn minus 1, right? So remember the properties of determinants, that the determinant of the product is going to be equal to the product of the determinants of those individual matrices. So this is just going to be equal to the determinant of the matrix 1, 1, 1, 0 all to the power of m is going to be equal to the determinant of this Fibonacci matrix, fn plus 1, fn, fn, fn minus 1. So these are just 2 by 2 matrices, no problem there. So the determinant of 1, 1, 1, 0 is going to be 1 times 0 minus 1 times 1, which is going to be equal to minus 1. So minus 1 to the power of n is going to be equal to fn plus 1 times fn minus 1 minus fn the quantity squared. So we get this very beautiful property that if you multiply the n plus 1th Fibonacci number with the n minus 1th Fibonacci number and you subtract the Fibonacci number in between them, then the difference is only going to be 1 or negative 1. So this is sometimes referred to as Cassinis Identity. And these differences are sometimes referred to as Cassini differences. So let's just look at an example of this, because this can be viewed as a very interesting property, because it's almost like a 2 things squared minus the same thing squared, almost the average, and the difference is only either positive 1 or negative 1 depending on where you are. All right, so let's just generate some Fibonacci's. So 0, 1, 1, 2, 3, 5, 8, 13. So let's pick a Fibonacci number here. Let's pick 5. All right, so fm plus 1 is going to be 8. Fm minus 1 is going to be 3 minus 5 squared. So what's that going to be equal to? So 8 times 3 is 24 minus 25, so that's going to be equal to minus 1. Let's just pick another one just for fun. So what's after 13? That's going to be 21. So let's pick 13 here. So let's do 8 times 21 minus 13 squared. So what's that going to be? So that's just going to be equal to 168 minus 169, so that's going to be equal to minus 1. So same as the previous one. And one can show if I pick 8, then I'm going to get a difference of positive 1. And it's going to sort of alternate between positive 1 and negative 1, depending on which index you actually choose here. So if you choose a even index, you're going to get 1. And if you have an odd index, then you're going to have a negative 1, which is actually pretty interesting. And there's one more property that can very easily be seen from the geometric intuition that we sort of built in the beginning. All right, so let's start off with our little squares. So there's our F1, there's our F2, here's our F3, here's our F4. So F5 is going to be a 5 by 5, right? And then the next one is going to be our 8 by 8. Right? So we're pretty much looking at areas here, right? So in terms of what we have here, so how can I view this in terms of the area? So it's very easy to see that the size of this length is going to be, of course, 8. And the size of this is going to be the next Fibonacci in sequence, right? Which is going to be 5 and 8 together, which in this case is going to be 13. So this is the sum of all of the area squared. So this is 1 squared, this is 1 squared, this is 2 squared, 3 squared, 5 squared, 8 squared. So all of those things added together. So we can rewrite that as 0 squared plus 1 squared plus 1 squared. Of course you don't need the 0 squared, but I just want it to be there. So we have 2 squared plus 3 squared plus 5 squared plus 8 squared is equal to, just from this picture, that's just going to be equal to 8 times 13. Right? So how can we rewrite that in very compact notation, right? So that's just going to be the sum from k is equal to 0. So in this case, this is 0, 1, 2, 3, 4, 5, and 6. So that's the sixth Fibonacci number, which is going to be 8, right? So fk. So that's going to be equal to f6, which is 8, multiplied by f7, the next Fibonacci in sequence. So of course you can do mathematical induction to extend that. And that should of course be fk squared. We can extend this to the sum from k is equal to 0 to n of fk squared is going to be equal to the kth Fibonacci number times the next one in sequence. And again, you can use mathematical induction to prove that the sum of the squares of Fibonacci numbers is equal to fk times fk plus 1. And we already proved before that the sum from k is equal to 0 to n of fk, just the sum of Fibonacci numbers, was just equal to f of k plus 2 minus 1. Now, of course, I extend you to investigate on your own. What about a formula for sum of k equals 0 to n of fk cubed? So what would be the closed formula for that? Because remember, we had a formula for the sum of k. So as I said, that's k plus 1 over 2. We have the sum of k squared, which is k plus 1, 2k plus 1 all over 6. These should be n's, of course. N, 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 and n. And we, of course, had shown that the sum of k cubed is going to be equal to n plus 1 all over 2 squared. So is there a nice pretty formula for the sum of cubic Fibonacci numbers? So I'll investigate you to sort of look that out, and if you can find that, post it in the comments below. Anyway, that's just some additional properties for the Fibonacci numbers. Hope you enjoyed.